Okay, finishing up chapter 23. So last time we kind of ended talking about the pleural membranes and pressures. This time we're going to get into actual respiration, pulmonary ventilation. There are 4 steps to respiration. It's the exchange of gases between both the atmosphere and the body cells. You have pulmonary ventilation, which is the movement of gases between the atmosphere and the alveoli. So that's the pulmonary ventilation, it's just breathing. Alveolar gas exchange is our external respiration. It's the exchange of gases between alveoli and blood. So this is the movement of gases. Pulmonary ventilation and gas transport, those are movement of gases. Alveolar and systemic gas exchange are actually exchange of gases. So alveolar exchange is between the alveoli and the blood. You then have gas transport, which is the transport of gases in the blood between the lungs and systemic cells. So this is going to be going both carbon dioxide from the cells, from the body tissues to the alveoli, and oxygen from the alveoli to the blood. Or I'm sorry, rather taking oxygen from the lungs to the cells and carbon dioxide from the cells to the lungs. Then at the cells, you have the systemic gas exchange, which is our internal respiration. So alveolar external, systemic internal. This is the exchange of respiratory gases between the blood and the systemic cells. This is just kind of a list of the net movement of respiratory gases. You should understand all of this. You should be able to know all 4 of these processes, what they're doing, and the movement of gases. So air containing oxygen inhaled into the alveoli during inspiration, oxygen diffusing into the pulmonary capillaries, blood from the lungs transports oxygen to systemic cells, that gets offloaded into the systemic cells from the systemic capillaries, carbon dioxide from the cells into the capillaries, carbon dioxide transported back to the lungs, carbon dioxide diffuses out through the alveoli, and then air containing oxygen is exhaled. Here it is, just a diagram representation. I think this might be on the worksheet that you have to fill this out. But yeah, it's exactly the same thing. You start over here with pulmonary ventilation, air coming in, goes to the tissues, and then back out. So breaking those down a little bit more. So pulmonary ventilation is your breathing. Again, that's just kind of like the inhale, exhale. It is air movement. There are 2 phases, your inspiration and your expiration. Inspiration is inhaling, expiration, exhaling. Shocking. Quiet breathing is eupnea. This is just kind of what you do normally. Just when you're not really thinking about it, when you're just sitting there, you're just doing eupneic breathing, just nothing remarkable at all about it. Forced breathing is vigorous breathing accompanying exercise. Autonomic nuclei in the brainstem will typically regulate that breathing activity. We'll see it's both in the medulla and in the pons. There are respiratory nuclei. Skeletal muscle contracts and relaxes, changing the thoracic volume. So both our internal, external intercostals, the posterior, superior, and inferior serratus, the diaphragm, your primary respiratory muscle, all these are going to work, as well as your scalenes, your SCM, so many other muscles work to change your thoracic volume. That helps to create a pressure gradient between the lungs and the atmosphere that allows for air to move down, because air is going to move down that pressure gradient. Air entering the lungs during inspiration, exiting during expiration. So the muscles of quiet breathing. Your diaphragm and your external intercostals contract for inspiration. The external intercostals and the internal intercostals are exactly what you would think. The internal are deeper, the external are more superficial. They run slightly different, they run perpendicular directions. The external opening and lifting the ribs more, the internal drawing them down. The diaphragm itself is going to flatten when it contracts. The external intercostals elevating the ribs, and then they relax for expiration. So this is the thing with breathing. If it's just normal quiet breathing, if you're just doing an inhale, that is an active process. It takes kind of muscles to expand the rib cage, but exhaling, they're just relaxing, and that relaxing is going to, because lungs have that elastic recoil, that's just going to draw the lungs back in on themselves and push that pressure out. The muscles of forced inspiration, so if you're just doing quiet breathing, really, in quiet breathing, your chest shouldn't move so much. Your belly and your ribs might expand out to the side, but you shouldn't have a big lift in your chest. When you inhale, the first thing that should happen is your diaphragm pulls down, and so your belly will distend and your belly will push out, but the ribs will stay fairly soft. When you're breathing strongly, though, your SCM, your scalenes, the pec minor, serratus posterior superior, all are going to contract for deep inspiration to actually lift the rib cage superior in the thorax. So they move it up, out, and forward, increasing that thoracic volume even more than the diaphragm and external intercostals already have. As well as the external, or the erector spinae contract. They run down your back and up towards the base of your skull, and they're going to help to contract and lift the rib cage. So muscles for forced expiration. Again, normal expiration, normal quiet breathing. It's not a forced process. It's a passive process. Expiration, exhaling is, but you can have forced expiration. Your internal intercostals, abdominal muscles, transverse thoracis, serratus posterior inferior are all going to help contract the during a hard expiration. So coughing, vomiting. They either pull the rib cage inferior, immediately posterior, or compress the abdominal contents. So either way, they kind of increase that abdominal pressure. Collectively termed accessory muscles of breathing when paired with the muscles of forced inspiration. There they are, just in a nice little diagram for you. Again, you should be able to kind of look and see how, based on their attachments and fiber directions, they're going to be lifting, expanding, or kind of drawing back in the case of the serratus posterior inferior, drawing back in the rib cage. Okay, volume changes in the thoracic cavity. So the thoracic volume changes vertically, laterally, and anterior posteriorly. So front and back, to the sides, up and down. The entire cage of the rib cage of the thorax is going to be expanding. Those vertical changes result both from the diaphragm movement, so it's going to be flattening down and moving inferior when it's contracted, and then when it returns back up, decreasing the vertical dimensions of the rib cage, of the thoracic cage, rather. For relaxed breathing, only small movements. For forced expiration, the abdominal muscle contraction causes large movement of the diaphragm superiorly. Again, that's forced expiration. Here is just a pictographic representation of that. Okay. Volume changes, lateral dimension changes. The rib cage elevation widens thoracically in inspiration. Depression narrows it during expiration. Changes due to activity, except for the muscles of the diaphragm. The diaphragm is not going to change the lateral dimensions of the rib cage, only the vertical. Anterior posteriorly, I misspoke on the diaphragm only being vertical. The anterior posterior changes. Inferior part of the sternum moves anterior towards inspiration, posterior during inspiration, according to activity level, except the diaphragm. Also, no, I did not misspeak. Okay, so now talking about Boyle's law. So now all that was just to kind of talk about how the thoracic cage is going to be changing shape. Because as it changes shape, it changes volume. And when volume changes, pressure changes. And that's how air moves. Remember, air moves down its pressure gradient. So Boyle's law talks about the relationship of volume and pressure. It says that at a constant pressure, or at a constant temperature, pressure of a gas decreases if volume of the container increases, and vice versa. So what's this saying is that as your pressure goes up, as the volume goes up, the pressure is going to decrease. So the more volume you have, the more space that you have, as long as you're kind of maintaining a constant temperature, you're going to have this decreased pressure. If you decrease your volume, that pressure, that gas that's inside of there is going to be, the particles are going to be knocking around faster. They're not going to have as much space to bounce around, so they're going to be hitting up against each other faster. It's going to increase the pressure in that container, in that area. If you download these slides, you should have this link. If it isn't, let me know and I will send it to you. I'll post it. It's just a video representation of Boyle's law. Because understanding the theory here is pretty important for being able to understand how air moves while we're breathing. So P1 and V1 represent initial conditions, P2 and V2 the changed ones. So it's an inverse relationship between gas pressure and volume. Basically saying that as one goes up, as volume goes up, pressure goes down. As volume goes down, pressure goes up. So an air pressure gradient exists when the force per unit area is greater than one place than another. That's going to create this pressure gradient. So having a higher pressure in one space versus a lower pressure in another space. And if they're interconnected, the air will flow from high to low until that pressure is equal. So in this one right here, you can see that they're connected and the pressure is already equalized. They're equal volumes, equal pressures. In this case, you have a smaller volume, which means higher pressure, and a larger volume, which means lower pressure. So since they're connected, you're going to have this air flowing down its pressure gradient. In this case, that's been reversed. You're decreasing your volume here for the pressure B, for the area B, which increases its pressure and pushes the air here. So this is how our lungs work, right? When they are equal to atmospheric pressure, there's really no movement. So at the very Beginning of inspiration, the end of the tip of inspiration, the bottom of expiration, the pressures are equalized. The atmospheric and lung pressures are equal. But we can increase the volume of our lungs by pulling down our diaphragm, by expanding our thoracic rib cage. And as we increase that pressure, we pull air from the atmosphere into our lungs. When we exhale, we decrease the volume of our rib cage. That then increases the pressure in our lungs, which pushes the air back up to the environment. So atmospheric pressure is the pressure of air in the environment. It will change with your altitude. Increasing the altitude equals thinner air, which is lower pressure. Essentially what's happening, so there's a misconception that a higher altitude has less concentration of oxygen. What it is because there's less pressure, it's more dispersed, and so there's still the same percentages of gases, but it's just harder to get in more oxygen because the air, there's not as much of a pressure difference, and so it's harder to get air in. So the higher up you go, the lower the pressure is going to be, and the closer it will start to get towards your intrapulmonary pressure. We'll see. At sea level, the value is 760, which is what we consider basically 1 atmosphere. I usually work with the atmospheres. It is unchanged in the process of breathing. So as you breathe, you are not changing atmospheric pressure. That is, you have to have like Superman lungs to do that. Okay, alveolar volume is the collective volume of the alveoli within your lungs. The intrapulmonary pressure is the pressure in the alveoli. This will fluctuate as you breathe. So it may be higher, lower, or equal to atmospheric pressure. Again, equal to atmospheric pressure at the end of inspiration and expiration. It, by the way, will change directly with breathing. So as you inhale, you increase alveolar and intrapulmonary pressure. As you exhale, you decrease these pressures. Intrapleural pressure is the pressure in the pleural cavity. So actually within that space in between those membranes. This will also fluctuate with breathing. So this fluctuates with breathing. The intrapulmonary pressure fluctuates with breathing. Atmosphere does not. This pressure should stay lower than intrapulmonary pressure to keep the lungs inflated. So the pressure within the alveoli, the intrapulmonary pressure, should be greater than intrapleural pressure to keep pushing against the thoracic walls. It's about 4 millimeters lower than intrapulmonary pressure between breaths. Volume changes create pressure changes, and air flows down its pressure gradient. We've said that a couple times. During inspiration, your thoracic volume increases, thoracic pressure decreases, so air flows in. Again, an indirect relationship between between volume and pressure. Volume increasing, pressure decreasing, air flows in. During expiration, thoracic volume decreases, thoracic pressure increases, air flows out. This is what? At the end of an expiration, yeah, so this is exhaling. They don't have quite as severe of a movement. Oh, there used to be 2 pictures. I think your book has 2 pictures, and they show inspiration and expiration. But sorry, I don't mean to keep bouncing back and forth between that. But yeah, you can see that you have the alveolar volume, so this is in your lung, the intrapulmonary pressure, atmospheric pressure on the outside, and then the intrapulmonary pressure in the pleural cavity. Or I'm sorry, intrapleural pressure in the pleural cavity. So inside of the lungs, at the end of an expiration, the pressure, the intrapulmonary pressure, and the atmospheric pressure are going to be the same. And then your intrapleural pressure will be still slightly less than the intrapulmonary pressure. And then when you inhale, that will start to change a lot. Okay, quiet breathing, inspiration. Your intrapulmonary pressure and atmospheric pressures are initially equal. So at the beginning of inspiration, they're going to be starting off being the same. Intrapleural, 4 millimeters lower. The diaphragm and the external intercostals contract, increasing thoracic volume. As volume increases, intrapleural pressure decreases. So between the pleural cavity, that pressure is going to decrease. The lungs pulled by the pleuris, so the lung volume increases, and the intrapulmonary pressure decreases. So now the pressure inside of your lungs in the alveoli is going to start to decrease as this lung volume increases. Because the intrapulmonary pressure is less than atmospheric, the air flows in until those pressures are equal. Typically, half a liter flows in as tidal volume. So just a normal, quiet breath. So your tidal volume, that's going to be about half a liter. And again, it's just your diaphragm and your external intercostals expanding the ribcage slightly. That opens up more space in the lungs, and that brings air in. Initially, the intrapulmonary pressure equals atmospheric pressure, again, at the beginning of your expiration. The pleural pressure is a little bit lower now. The diaphragm and external intercostals relax, decreasing the thoracic volume. Again, they're just relaxing. They're not really contracting or anything because that would just increase thoracic volume. As the volume decreases, pressure increases inside the pleural cavity. The elastic recoil of the lungs pulls the lungs inwards. The alveolar volume decreases. Intrapulmonary pressure starts to increase as well. Since the intrapulmonary pressure is greater than atmospheric, air flows out. And again, it's about the same tidal volume. There you go, comparing the two. You can see that in an inspiration, your diaphragm is nice and flattened here. That's weird. I don't know why why the diaphragm is flattened for the expiration, but okay. Maybe this is the beginning of it and that's the end. So you have, oh yeah, that's exactly what happened. So you have, starting here with the beginning of inhalation, the top of the inhalation, the beginning of the exhalation, and the end of the exhalation. You should know these pressures. You should know the pressure changes, the volume changes, and what muscles are working to do that, as well as the different cavities that are where those pressures are. The cavities that are changing volume and the pressures that are associated with them. There we go. Here is just a different representation of that same very thing. This is the volume changes. These are the pressure changes. The red is the intrapulmonary. The blue is the intrapleural. This is inhalation. That is exhalation. Okay, looking at nervous control of breathing. So the autonomic nuclei within the brain coordinate breathing and the respiratory center of your brain stem, both in your medulla and in your pons. You have your medullary respiratory center. It has both the ventral respiratory group, the VRG, and the dorsal respiratory group, the DRG. Ventral is in the anterior, dorsal is posterior, if you remember your body regions. The pontine respiratory center in the pons is also known as the pneumotaxic center. We'll see that these two regulate different portions of breathing. Different aspects of breathing, rather. The brainstem neurons influence the respiratory muscles. The VRG synapse with the lower motor neurons of the skeletal muscles in the spinal cord. The lower motor neuron axons project to the respiratory muscles, the diaphragm innervated by the phrenic nerve, and the intercostals by the intercostal nerves. You'll have chemoreceptors monitoring changes in concentrations of hydrogen, carbon dioxide, and oxygen partial pressure, the PO2 and PCO2. That P stands for pressure, or partial pressure, we'll see. So the partial pressure of carbon dioxide and oxygen in the blood, mostly carbon dioxide. You have both central and peripheral chemoreceptors. Central are in the medulla, monitoring the pH of the cerebrospinal fluid. CSF changes are caused by changes in blood PCO2. As you increase your CO2, you're decreasing your pH. You're making it more acidic. So carbon dioxide diffuses from the blood to the cerebrospinal fluid, where carbonic anhydrase, that's an enzyme, is. Sorry, I was like, I thought for a second that I was missing a word. No, that's just where carbonic anhydrase is. That builds carbonic acid from carbon dioxide and water. So carbon dioxide and water and the presence of carbonic anhydrase builds carbonic acid. That, again, will lower the pH of your blood and your CSF, which stimulates these central chemoreceptors. The peripheral chemoreceptors are in the aortic and carotid bodies, so the only difference between the central and peripheral is the location, mainly. The central and medulla, and these are in the aortic and carotid. These are stimulated in changes by hydrogen or respiratory gases in the blood, so hydrogen or carbon dioxide. Both of these will cause the blood pH to start to drop. Carotid chemoreceptors send signals to the respiratory center via the glossopharyngeal nerve, and aortic chemoreceptors send signals via the vagus nerve. Other ones are irritant baroreceptors and proprioceptors. The irritant receptors, we saw the carina that are stimulated by particulate matter. Baroreceptors in the pleura and bronchioles respond to stretch, just like there are baroreceptors in the heart that are responding to the heart stretch. There are ones in the lungs as well. And proprioceptors in muscle and joints stimulated by body movement. If you've ever done one of those things where you kind of start to move your body joints, it actually initiates your nervous system to increase your breathing, and it changes pressures within your body when you start to move joints. Here is kind of how the respiratory center relates to its effectors, or stimulants rather. You should understand their pathways. Okay, physiology of quiet breathing. How does it actually happen mechanically, or functionally rather? Similar. Inspiration begins when the VRG, the ventral respiratory group, inspiratory neurons fire spontaneously. So it is a spontaneous firing of the channels. Signals are sent from the VRG to nerve pathways exciting skeletal muscles for about 2 seconds. They get a 2-second firing pattern. And the diaphragm and external intercostals contract, causing air to flow in. So there's this 2-second firing, the muscles start to contract, air starts to come in. The quiet expiration occurs when that VRG is inhibited. So the signals from the inspiratory neurons are relayed to the VRG expiratory neurons. Those expiratory neurons send inhibitory signals back. They create a negative feedback loop. And this signal is no longer sent to inspiratory muscles for about 3 seconds. That causes the muscles to relax and air to flow out. So you get this 2-second signal exciting the muscles, causing inspiration, and then a 3-second inhibitory signal causing them to relax. Respiration rate for normal quiet breathing it's called eupnea. It's 12 to 15 breaths per minute. So just normally, as you're sitting and breathing, you should have about 12 to 15 breaths per minute. If you have less functional alveoli, if your respiratory membrane is damaged, if you are not your respiratory zones are not conducting or exchanging gases as effectively, your respiratory rate may go up. So to get the same amount of gas exchange as someone for the same size, weight, all the same things as you, if you have a less functioning respiratory system, you may have to breathe faster than someone who, let's say, maybe they only do 10 breaths a minute to get the same amount of gas exchange. So that's just an aside, 1 breath per minute kind of thing. The Pontine Respiratory Center facilitates smooth transitions between inspiration and expiration. So it does not necessarily regulate the breath itself. That's in the Medullary Respiratory Center. This just kind of makes sure that you have smooth transitions. It's not this kind of erratic breathing. Apnea is the absence of breathing. It can occur voluntarily, swallowing or holding your breath. We can just stop breathing. It can be drug-induced, and it can result from neurologic disease or trauma. Sleep apnea is the temporary cessation of breathing during sleeping. It's a common cause of snoring. Okay, still talking about reflexes now that alter breathing rate and depth. Those chemoreceptors that we mentioned, they alter breathing by sending signals to the DRG, which then get relayed to the VRG. The VRG triggers changes in the rhythm and force of breathing. So rate changes by altering the amount of time in inspiration and expiration. That's as depth changes by stimulation of accessory muscles. They can make you breathe faster and deeper or slower and shallower. Ventilation will increase in response to central chemoreceptors detecting increase in concentrations of hydrogen or peripheral chemoreceptors detecting increase in blood hydrogen or PCO2. So again, both of these would be signaling that the pH of the blood is starting to decrease, it's becoming more acidic, and so your body will increase ventilation to try and exhale that excess CO2. Increased ventilation expels more CO2, returning conditions to normal. Ventilation decreases if chemoreceptors detect decreases in hydrogen or PCO2. So as your blood becomes too basic, it goes beyond that 7.45, it's going to start to slow down the respiratory rate to try and keep some of that CO2 so that it can be converted to carbonic acid. Blood PCO2 is the most important stimulus affecting breathing. It is not your oxygen. It is not your partial pressure of your oxygen. It is the partial pressure of carbon dioxide. Raising the blood PCO2 by 5 bars of pressure causes doubling of the breathing rate. So a small change, just 5 millimeters of mercury pressure change, doubles your rate of breathing. CO2 fluctuations influence the sensitive central chemoreceptors because our CO2 rate does not change, or our CO2 concentration does not have big fluctuations. We'll see that our oxygen PCO2 or PO2 fluctuates quite a lot. There's a large range that our body goes through, but with our PCO2, it does not. It stays very, very much in a small range, and so it's much more accurate to determine what our rate of breathing should be than oxygen, which kind of can dip and drop, or can soar and drop. So CO2 fluctuations do influence those sensitive chemoreceptors. Carbon dioxide combines with water, makes carbonic acid. CSF lacks protein buffers, and so its pH change triggers reflexes. So it can happen very quickly. There aren't those protein buffers like the blood has. Blood PO2 is not sensitive regulator of breathing. Arterial oxygen must decrease from 95 to 60 to have a major effect independent of PCO2. So you have to really lose a lot of blood oxygen before it starts to count as a chemoreceptor, before the body responds to it. When PO2 drops, it causes peripheral chemoreceptors to be more sensitive to blood PCO2. So even as it's dropping, they just start to monitor the CO2 even more, because that's again going to be its best way of monitoring the pH. Hypoxic drive. Normally the most important stimulus affecting breathing rate and depth is PCO2. Hypoxic drive is when PO2 levels become the stimulus for breathing. It can occur in some respiratory disorders such as emphysema with a decreased ability to exhale carbon dioxide. So essentially what happens is the carbon dioxide levels in the blood will remain elevated for a really long period of time, and so the chemoreceptors become less sensitive to it. They just become numb to the fact that, okay, yeah, PCO2 is just really high, and so by default they just go to PO2, allow that to stimulate them. Administering oxygen can elevate PO2 and interfere with that person's ability to breathe on their own. So actually giving them oxygen will trick their medullary respiratory center to alter their breathing rate, possibly even down lower, causing them to not be able to breathe. With emphysema, they lose the ability to really exhale properly. They can't really fully let their lungs relax, and so the CO2 levels build up in their blood. Okay, reflexes that alter breathing rate and depth. Through other receptors, you have joint and muscle proprioceptors stimulated by body movements. They signal the respiratory center to increase breathing depth. Think about like when you're waking up and you stretch in the morning, you take a big yawn. Baroreceptors within visceral pleura and bronchial smooth muscles send signals to the respiratory center when they become overstretched. So when they start to detect that you're kind of reaching the limit of your inhale, they initiate the inhalation reflex, the Ehring-Brewer reflex. Inhalation reflex is perfectly fine. You don't have to remember that name. The inhalation reflex shuts off inspiration and protects against overinflation. And then your irritant receptors are going to initiate sneeze and cough reflexes. Exaggerated intake of breath followed by the closure of the larynx, contraction of abdominal muscles, and abrupt opening of vocal cords. Your higher brain centers can get involved. Your hypothalamus can increase the breathing rate if the body starts to become too warm, working through that respiratory center. Again, the hypothalamus is a kind of control center for all things. The limbic system alters it in response to emotions. If you start to get sad or depressed or really excited, your breathing rate will start to change. The frontal lobe controls voluntary changes, so you can bypass the respiratory center and stimulate those lower motor neurons of the diaphragm and the phrenic nerve and the intercostal nerves directly. The respiratory system has some smooth muscles and glands, all controlled by the autonomic brainstem nuclei. The breathing muscles are skeletal muscles, though, controlled by the autonomic nuclei, the cerebral cortex, and the somatic nervous system, since they're skeletal muscles. Thus, both reflexive and conscious controls of breathing, as we said. Okay, airflow, pressure gradients, and resistance. So I'm getting a little bit more into probably what you love the most about this is the air pressure and air movement stuff. So airflow is the amount of air moving in and out of the lungs with each breath. It depends on both a pressure gradient and resistance. So the pressure gradient established between atmospheric pressure and interpulmonary pressure, the pressure in the air, the pressure in the lungs, and resistance that occurs to conditions within the airway, lungs, and chest wall. If this looks familiar to blood flow, it's because those are also dependent on your pressure gradient and your resistance. Here's this thing that we've seen. Flow equals the change in pressure over resistance. This is again going to be the difference between air and lungs. Flow is directly related to pressure and the pressure gradient, and inversely related to resistance. So directly related to pressure and then inversely related to resistance. If pressure gradient increases, airflow increases. Resistance increases, airflow decreases. Between the air and the lungs can be changed by altering the volume of the thoracic cavity. So we don't change it. This is something that sometimes people get confused with. We don't change the pressure in our lungs. We change the volume of our thoracic cavity, and that changes the pressure. So we can adjust the volume of our thoracic lungs, and from that, the pressure will start to change. Small volume changes a quiet respiration, allow 500 mils, half a liter of air to enter. accessory muscles are used, volume increases even more, and airflow will increase due to that greater pressure gradient. As you start to use more than just your diaphragm and your external intercostals, as you start to use some of those accessory muscles that are going to increase the size of your thoracic rib cage even more, you're going to increase that pressure gradient, and it's going to bring air in faster. So factors that increase the difficulty for moving the air can be altered by the change in the elasticity of the chest wall and lungs. If it can't expand and contract, if it's not as compliant, then it won't be able to move the air as easily. Change in bronchial diameter, so as bronchodilation or constriction happen, you'll increase or decrease airflow, and collapse of alveoli. So that surfactant is supposed to be in there to keep them open, but sometimes that can malfunction, it can stop producing. There are some alveoli that are just always collapsed. That's just a normal physiologic dead space. But that does make it harder to breathe then. So chest wall increases resistance, chest wall elasticity decreases with aging and disease. You can have vertebral malformations, can decrease elasticity. Arthritis in the thoracic cage will cause movement to be limited, and replacement of elastic tissue with scar tissue. It's called pulmonary fibrosis. I had a friend, it wasn't pulmonary fibrosis, she got into a bad car wreck, and some of the muscle tissue in her intercostals was replaced with scar tissue, and so she couldn't, her lungs wouldn't expand because she had this scar tissue that was holding her ribs together, so she had to have a massage therapist go in there and break up that scar tissue. And you can just kind of take your fingers and rub them in between the spaces of your ribs and see how sensitive that is, and just imagine, and that's probably healthy muscle, that's not, hardened scar tissue that you have to break up. It was tough. So the bronchial diameter varies inversely with resistance. Constriction, so shrinking the diameter, increases resistance. Dilating the diameter decreases resistance. Bronchoconstriction is caused by parasympathetic activity, histamine, or cold. Occlusion by excess mucus or inflammation. So all of these things will shrink or cause bronchoconstriction or occlusion. Dilation is sympathetic stimulation, epinephrine, those things will cause it to open. Again, sympathetic is fight or flight. As you are running, as you are trying to fight, you are increasing your metabolic activity, which increases your body's need for oxygen. Bronchodilation will bring in more oxygen. Collapsed alveoli increase resistance. It can occur if the alveolar type 2 cells aren't producing that surfactant. The high surface tension of the alveoli is not overcome, and so they'll collapse in on themselves. Important factor for premature infants, you may have kind of heard that they'll give them some of that pulmonary surfactant to help them keep it open. It's referred to as respiratory distress syndrome. Compliance, then, is the ease with which the lungs and chest wall expand. So it's kind of like the opposite of resistance in a way. So it's not what's making it harder, it's how easy will the chest wall expand. Determined by the surface tension and elasticity of the chest and the lung. Easier the lung expands, the greater the compliance. Several conditions can increase that resistance. Decrease in bronchial lumens, so something like asthma. Decrease in compliance, pulmonary fibrosis, emphysema. The result is a need for more forceful inspirations, and more forceful inspirations of respiratory disorders require higher amounts of energy. So as your compliance decreases, as your resistance increases, it takes more energy to breathe, to take air in, to bring air in. That will then make you more tired. It can cause a 4 to 6-fold increase in the energy need, from 5 to 25% of the body's total energy expenditure. So individuals with these conditions can become exhausted. I always say that, I tell the story of a couple of years ago I had pneumonia. And 27, 28-year-old something yoga teacher, very normally healthy otherwise, but trying to recover from pneumonia, I would have to lean against, just trying to stand and talk, I would break out into a full sweat. So I would have to lean up against the wall and hold myself up just to stand and talk. Because my body was putting so much energy just into trying to breathe. It was exhausting. Okay. Pulmonary ventilation, moving back into this and talking about some of the volumes and rates. So pulmonary ventilation is the process of moving air into and out of the lungs. Amount of air moved between the atmosphere and alveoli in 1 minute. The tidal volume is the amount of air per breath. That's just kind of your normal air in, air out. It's usually about 0.5 mil, right? 500 liters. The respiration rate is the number of breaths per minute. If you multiply those two, you get your pulmonary ventilation. So typically, we're getting about 6 liters per minute of air in and out. Now, we can talk about as it travels there are different zones within that. So the anatomic dead space is your conducting zone. This means that there's no exchange of respiratory gases, and you're going to have about 150 mils of air left in here. So about 150 just kind of sits there. In alveolar ventilation, this is the amount of air that reaches the alveoli per minute. So to find that, you subtract your tidal volume, which you're actually breathing in, minus the anatomic dead space. Again, this is where air just sits. You know, you inhale and you breathe in 500 mils, but only about, 350 will reach your lungs, will reach the alveoli. There's about 150 that sits in the conducting zone in those passageways. Deep breathing maximizes alveolar ventilation. So the more you breathe in, the more air you're going to be, not just volume-wise, but also force-wise, bringing air in. Just a normal, regular kind of resting breath. There's not a whole lot of force behind that, so it leaves air in this anatomic dead space. The physiologic dead space is, again, kind of thinking the difference here, anatomic versus physiologic. The physiologic dead space is your normal anatomic dead space, plus any loss of alveoli. That would be considered somewhat abnormal. Some disorders decrease the number of alveoli participating in gas exchange, such as pneumonia, due to damage of the alveoli or changes in the respiratory membrane. Your anatomic dead space equals a physiologic dead space in a healthy individual where loss of alveoli is minimal. So essentially they should be about equal. Hold on. Yeah. Moving through that. So basically you should just understand that the anatomic dead space is the conducting zone. That's normal. There's about 150 mils left in there. To figure out how much air gets to your alveoli, you subtract your tidal volume from your anatomic dead space. You can multiply it by your respiration rate if you want to, but really I would probably just want you to tell me how many mils of air is reaching that. The physiologic dead space, you should connect physiologic with loss of alveoli. That can increase with disease. That's what I want you to know. Spirometer measures respiratory volume, can be used to assess respiratory health for standard. Standard values are available for people of different ages to compare against. 4 volumes, your tidal, inspiratory reserve, expiratory reserve volume, and residual volume. Again, the tidal is just that normal inhale, exhale at rest. The inspiratory reserve volume is the amount of air that can be forcefully inhaled beyond the tidal volume. So you can inhale, but then you can deeply inhale. Same thing with exhale. You can exhale, but then you can really exhale. IRV measures compliance, so the ease with which your lungs will stretch. ERV measures elasticity, the measure of which your lungs will recoil. So compliance is stretching, elasticity is recoiling. I think a lot of people will confuse those two. The residual volume is the amount of air left in the lungs after the most forceful expiration. You can never get rid of this. There will always be a small amount of air left in your lungs that prevents them from fully collapsing. And again, when you think about small amount of air left in your lungs, you should think small amount of air left in your alveoli. So that residual volume will always be in there even after your ERV. 4 capacities, IC, FRC, vital capacity, and total lung capacity. I don't really get into these too much. If you start getting into like pulmonary medicine, you'll go into much more depth with these. Really, I'm concerned with you knowing these 4 volumes. The capacities not as much concerned with it. Similar to these measurements, I'm not going to really get into these so specifically, other than, can you just straight up define them? Percent of vital capacity can be expelled at a set period of time, greatest amount of air that can be taken in. You should know those basic definitions. Here's a nice little graph that represents them just so you can kind of see them compared to each other. Okay, now getting into chemical principles of gas exchange. This is a little bit more fun, I think. So partial pressure is the pressure exerted by each gas within a mixture of gases. What this is saying is that you can have atmosphere, which is nitrogen and oxygen and carbon and hydrogen and all a bunch of little things. And collectively, their total pressure, collectively they make up 100% of the pressure in that gas. but each of those individual elements is going to have its own partial pressure. So the total collective pressure is 100%, but 76 is going to be no, that's not right. 71 is going to be nitrogen. No, yeah, 76 is going to be nitrogen. 21 is going to be oxygen. 0.03 is going to be carbon dioxide. There's going to be small amounts of other gases that are available in the atmosphere, and they can each be measured independently. If like maybe it's easier to think about like if you have a pool or if you have a fish tank and you do those little tests to kind of measure the different concentrations of chemicals in the water. There's each chemical for the phosphorus, the nitrogen, the potassium, whatever you're measuring. You're going to have to measure each one individually because they all have their own concentrations. It's the same thing with the atmosphere. So it's written with a P followed by the gas symbol. We've already seen PO2 and PCO2. And it's important to note, this is the important thing here, is that each gas moves independently down its own partial pressure gradient during gas exchange. This is why carbon dioxide and oxygen will be moving in different directions in internal and external respiration. Atmospheric pressure is 760 millimeters mercury at sea level. Total pressure of all gases collectively exert in the environment. So collectively, all of the gases and these major and minor gases collectively exert this much pressure at sea level, but then each individual one is going to be contributing a small amount. 78, I know, it's close. So partial pressure. So total pressure times the percent of the gas equals the partial pressure of that gas. So nitrogen is 78.6% of gas in the air. If you multiply the total pressure at sea level times the concentration of nitrogen, you get the partial pressure of nitrogen. Added together, they equal the total partial pressure, the total atmospheric pressure. So what Dalton's law just says is the total pressure of a mixture of gases is equal to the sum of the individual partial pressures. So if you add up the partial pressures of nitrogen and hydrogen, oxygen, carbon dioxide, they will all equal the 760 or whatever that atmospheric pressure is wherever you're measuring it. So these partial pressure gradients, they exist when a partial pressure for a gas is higher in one region than it is in another. Gas will move from that region of high partial pressure to the lower partial pressure until they start to equalize. And both types of gas exchange depend on those gradients. Again, the alveolar and the systemic gas exchange, external and internal, depend on that. So reasons partial pressures in alveoli differ from atmospheric partial pressures. The air from the environment mixes with air remaining in the anatomic dead space. The oxygen diffuses out of the alveoli into the blood. Carbon dioxide diffuses from the blood to the alveoli. And more water vapor is present in the alveoli than in the atmosphere. Within the alveoli, though, the percentage of partial pressure of oxygen is lower than the atmosphere. The percentage of partial pressure of carbon dioxide is higher than in the atmosphere. And the partial pressure of the respiratory gases normally stay constant. So in systemic cells, partial pressure gases reflect cellular respiration. As they use more oxygen, they produce more carbon dioxide. Percent of O2 is lower and CO2 is higher than in the alveoli, in your systemic cells that is. And under resting normal conditions, the partial pressures remain constant. So basically what this whole thing about remaining constant, it's saying that that's basically homeostasis, right? Is that there really shouldn't be these big fluctuations. If you're at rest, if you're not having these big bursts of energy, of energetic need, then relatively these concentrations should stay pretty normal. In circulating blood, gas partial pressures are not constant though. Your oxygen enters blood in the pulmonary capillaries, carbon dioxide leaves, oxygen leaves blood systemic capillaries, carbon dioxide enters. So in the blood, that's where things are fluctuating, that's where things are changing. But within the cells, within the alveoli, it should pretty much stay the same as long as the circulatory system is functioning properly. Okay, so looking kind of at this, I think some of these will break it up a little bit more. But here you can kind of go ahead and see the partial pressures. So saying that from the alveoli, this PO2 in the alveoli is 104, and the PCO2 is 40. But in the blood, the PO2 is 40, and the PCO2 is 45. So it's not a huge gradient for carbon dioxide, but it is still higher CO2, higher PCO2 in the blood than the alveoli, so CO2 will move around. Much steeper gradient for oxygen, 104 to 40, so oxygen will move down its gradient as well into the bloodstream. Then at systemic cells, you can see it switches. In systemic cells, you have the PO2 of 40, PCO2 of 45. In the blood, you have a PO2 of 95, a PCO2 of 40. So this carbon dioxide will move into the bloodstream as oxygen moves out and down its gradient. Okay, getting into some more about gas transport and gas exchange. So gas solubility and Henry's law. Henry's law says that at a given temperature, the solubility of a gas in liquid is dependent upon the partial pressure of the gas in the air, which we calculated with Dalton's law, and the solubility coefficient of the gas in the liquid. This just says how easily something will dissolve in that liquid. So basically saying you have to have something that can easily dissolve and have the pressure to make it dissolve. Think carbon dioxide in a soda. You know, when you open up a soda or something that's been carbonated, you have that kind of burst of bubbles, and it all kind of comes out, and eventually it starts to become flat. Because you're opening up the top, and if you leave the top off, the pressure has been released, and so carbon dioxide can then be released from the gas. It can be released from the liquid. Partial pressure is the driving force moving gas into the liquid, determined by the total pressure and percentages of gas in the mixture. Again, CO2 force into drinks under high pressure. That coefficient is the volume of gas that dissolves in a specified volume of liquid at a given temperature and pressure. It's a constant that depends upon interactions between molecules of the gas and the liquid. So gases will vary in their solubility. Carbon dioxide is about 24 times as soluble as oxygen. Nitrogen is half as soluble as oxygen, so it should tell you that it is not soluble at all. It does not normally dissolve in blood in any significant amounts. Gases with low solubility require larger pressure gradients to push the gas into the liquid. Okay, so this should tell you that carbon dioxide is more likely to be dissolved in the bloodstream, in the plasma, than oxygen. You can have decompression sickness, the BINS. It occurs when a diver is submerged in water beyond a certain depth and returns too quickly to the surface. Nitrogen forced into the blood due to the higher pressure. So as you go down, as you go deeper into the water, you're increasing the pressure, and as you increase just the pressure or the atmospheric pressure around you, that will force nitrogen to dissolve into your bloodstream. And dissolved nitrogen bubbles out of solution while still in the blood and tissues. As you come back up, you're relieving that pressure, and it can start to release. Treat with hyperbaric oxygen chambers. The partial pressure gradient for oxygen becomes increased. Additional oxygen can dissolve into your blood plasma. And can be used for carbon monoxide poisoning as well. Okay, alveolar gas exchange, external respiration, looking at the actual partial pressures of gases now and how this is going to happen. So the movement of oxygen. So the PO2, the partial pressure of oxygen in your alveoli, is 104. The PO2 of the blood entering pulmonary capillaries from pulmonary arteries is 40. Oxygen will diffuse across the respiratory membrane from alveoli to the capillaries down that partial pressure gradient, and it continues until the blood PO2 equals that of the alveoli. The levels remain constant as fresh air continuously enters. So again, we're constantly breathing in and out, in and out. These capillaries are wrapped around, millions of these alveoli, and so they're able to kind of retain this constant exchange. Movement of CO2, PCO2 in the alveoli is 40. In the blood, it's 45. It's going to diffuse from the blood into the alveoli down its pressure gradient. Continues until they equal, and it remains constant. Okay, anatomic features of the membrane contribute to its efficiency: the large surface area and the minimal thickness. So it's a lot of surface area. You have these alveoli, 300 to 400 million per lung, packed in there, wrapped around each other, stacked on top of each other. So a lot of surface area, very minimal thickness. As well as ventilation, perfusion, coupling. That's going to determine your efficiency here. And this is basically saying how well paired are both your circulatory system and your respiratory systems. This is the ability of bronchioles to regulate airflow and arterioles to regulate blood flow. So ventilation and perfusion. Ventilation changing bronchodilation or constriction. Perfusion changing dilation or constriction of the vessels. Dilation in response to increased PCO2 and dilation either response to decreased PCO2 or increased PO2. So emphysema, it causes an irreversible loss of pulmonary gas exchange surface area. Inflammation of the air passageways distal to the terminal bronchioles. Distal, note that, to the terminal bronchioles. Widespread destruction of pulmonary elastic connective tissue, dilation and decreased total number of alveoli, and inability to expire effectively. In most cases, it's caused by smoking, rarely from an alpha-1 antitrypsin deficiency, so a protein deficiency. But essentially, you're having this loss of alveoli, this physiologic dead space is going to increase extensively. You're going to lose your elasticity. It's going to be really hard for your lungs to exhale. Here is just showing kind of the differences between ventilation and perfusion. So in this one, you're having an increased ventilation, decreased ventilation, increased perfusion, decreased perfusion. Certain diseases decrease the efficiency of oxygen and carbon dioxide exchange due to decreased number of alveoli, thickened respiratory membrane, changes in ventilation perfusion coupling. Ultimately, they result in decreased PO2 and increased blood PCO2. My grandmother had chronic obstructive pulmonary disease, COPD. It's exactly what it sounds like. It's just a generic respiratory disorder. And so when she was at the end of her life, because that is what killed her, she had about 17 to 20% lung function. So it's a tough thing because, again, as soon as you can't breathe, you lose all of your energy. Your body loses all of its ability to bring in oxygen, or a lot of its ability to bring in oxygen for just normal repair and maintenance, let alone trying to fight any kind of infection or disease. Okay, moving into internal respiration. The oxygen diffuses out of systemic capillaries to intersystemic cells. Gradient derives that process. So we're in, again, internal respiration here. So the PO2 in systemic cells is 40, and capillaries it's 95. Continues until the blood PO2 is 40. Systemic cells are going to stay fairly constant. Oxygen delivered at the same rate it's used unless engaging in strenuous activity. So you have this constant supply of oxygen being delivered. Movement of CO2 diffuses from systemic cells to blood. Partial pressure gradient driving the process. PCO2 is 45, PCO2 is 40 in the systemic capillaries, and it's going to diffuse. So we kind of did this. Here it is in a slightly different representation. So this one is monitoring PCO2, this one is PO2. Up here you have your alveolar gas exchange, and down here is systemic gas exchange. You should be very comfortable with this process, with these pressures, knowing what they are and how they drive exchange. Okay, so transporting oxygen. This is the blood's ability to transport oxygen, depends on the solubility coefficient of oxygen. This is very, very low, and so very little oxygen dissolves in plasma. So really what we rely on is hemoglobin. The iron of hemoglobin attaches to oxygen. There are 4 oxygen per hemoglobin molecule, and what is it? 200, 300 million hemoglobin per red blood cell. About 98% of your oxygen is bound to hemoglobin, so all of your oxygen essentially is bound to it. HbO2, oxyhemoglobin, is with bound. HB is deoxyhemoglobin, meaning it does not have any oxygen bound to it. You can measure them with a pulse oximeter. It's non-invasive and direct way, applied to a finger or an earlobe. I worked again in veterinary medicine, so we put them on the dogs. We would always put them on the animals' tongues. You do have to make sure that they stay wet, though, if you do it on the tongue. If the tongue starts to dry out, then it can get an improper reading. This is one of the things, getting a pulse oximeter for COVID patients so that they can measure, because sometimes you feel perfectly normal and then you realize, oh, I'm getting very, very little oxygen to my actual cells. So a pulse oximeter can help you to monitor your oxygen delivery. Carbon dioxide has 3 means of transport, meanwhile. CO2 dissolved in the plasma is about 7%, so there is some that gets dissolved in the plasma because CO2 has a higher solubility coefficient. 23% of it is going to be bound to the globin portion of hemoglobin, and 70% is going to be converted to bicarbonate and dissolved into your plasma. Essentially what happens is the CO2 will diffuse into erythrocytes, combine with water to make bicarbonate and hydrogen ion. The bicarbonate diffuses into your plasma, and then it turns back into CO2 when it moves through pulmonary capillaries, and that process becomes reversed. It goes back, the bicarbonate will go back into red blood cells, get converted into CO2, and then exhale out. So here you can kind of see you have your CO2 being brought in the presence of carbonic anhydrase. It's splitting and making bicarbonate. It does that with a chloride exchange mechanism. And then when you get back to the lungs, your bicarbonate is imported back into the red blood cell, converted to CO2, and then released out. So hemoglobin is going to not just transport the oxygen and the carbon dioxide, but also some hydrogen ions. These two are both bound to the globin. These attach to each of the irons. 4 irons per hemoglobin. I'll say it one more time. Binding of one substance will cause a change in the shape of the hemoglobin molecule. This is really interesting because the hemoglobin, these are microscopic, just minuscule little things. And so when you bind them, when you have two things binding together and combining, it forces a conformational change. It has to change its shape. And so when it starts to change its shape, it influences the ability of hemoglobin to bind or release those other substances because they're going to be already there or they might be coming there. And so as it starts to change its shape, it's going to make it easier or harder. We can measure this with the oxygen hemoglobin saturation curve. It measures how much oxygen is bound to our hemoglobin, up to 4 molecules. 1 on each iron. The percent O2 saturation of hemoglobin is crucial. It's the amount of oxygen bound to available hemoglobin, and that's, again, how it's going to be transported. Saturation increases as PO2 increases. Increasing your pressure of oxygen, the amount of oxygen, the concentration of oxygen, however you like to think about it, is going to increase the binding of oxygen to hemoglobin. This is called the cooperative binding effect, such that each oxygen that binds causes a change in hemoglobin, making it easier for the next oxygen to bind. So this is a conformational thing. It's not necessarily an electrical or a chemical thing. It's just that as an oxygen binds, it makes hemoglobin change its shape slightly, and that change in shape will allow for other oxygen to bind easier. You can graph it in an oxygen hemoglobin saturation curve. Okay, so here's this curve. You can see the PO2 over here, the percent of oxygen saturation of hemoglobin. It gets graphed this way. So basically it's saying that at lower concentrations of oxygen, you're going to have much more rapid binding to hemoglobin. But at a certain point, once you kind of start to hit 98% of oxygen, of hemoglobin saturation, it can really only take so much more. It really can't take that much more. So even so basically what it says is that small increases in PO2 at the beginning will cause for greater oxygen binding to hemoglobin, but at a certain point, it doesn't matter how much, even once you get over 100 PO2, once your PO2 gets to 105, you're still only going to be at 98. That's about the max hemoglobin saturation that you can reach. Oh, sorry. Okay, large changes occur with small increases of PO2 at lower partial pressures. At a PO2 higher than 60, only small changes occur. Hemoglobin saturation is about 98% of the pulmonary capillaries, while PO2 is at 104. So again, 98% is about as much as you can get. You can only reach 100% at pressures above 1 atmosphere. So again, in a hyperbaric oxygen chamber where you're really just pumping that pressure. You can use the graph to determine saturation at a given PO2. At 5,000 feet, the alveolar PO2 is 81, corresponds to a hemoglobin saturation of about 95. At 17,000 feet, the PO2 is 40, which is about 75 hemoglobin saturation. You can get altitude sickness, which is adverse physiologic effects due from an increase in alveolar PO2 and low oxygen saturation, including headache, nausea, pulmonary edema, cerebral edema, when you go too high, too fast. The oxygen, some, not all, of the oxygen is released from hemoglobin at systemic capillaries. So some, but again, not all. We do hold on to some of it. 98% saturation as it leaves the lungs, about 75% after passing systemic cells. So really, when we say some, not all, we mean a very small sum. Only 20 to 25% of transported oxygen is released. The rest is oxygen reserve that remains bound to hemoglobin after passing through systemic circulation. It provides a means for additional oxygen to be delivered under increased metabolic demands, and vigorous exercise produces a significant drop in saturation. Blood leaving the capillaries is only about 35% saturated. So there's a much larger drop due to that increased metabolic demand during exercise or strenuous activity. Temperature and hydrogen binding to hemoglobin can also affect hydrogen saturation. So elevated temperature diminishes hemoglobin's hold on oxygen, and hydrogen ions bind to hemoglobin and cause a conformational change that decreases oxygen affinity and oxygen release. That's called the Bohr effect. These two things, like think about when you're doing like exercise, you're getting warmer and you're developing or producing more hydrogen ions. And so both of these things, like when you're exercising, it's going to actually increase your oxygen offload. Yeah. And that's good because you want to have increased oxygen offload at the tissues during exercise so that you can have more oxygen to use. So increased temperature and increased hemoglobin, or increased hydrogen binding to hemoglobin, will allow for oxygen to be released easier. 2,3-BPG is a molecule in erythrocytes. It binds to hemoglobin, again causing release of additional oxygen. Certain hormones stimulate the erythrocytes to produce that molecule. Thyroid hormone, epinephrine, growth hormone, testosterone. CO2 binding to hemoglobin causes more release of oxygen from that hemoglobin. So again, think like when you're in the cells, you have hydrogen binding, you have carbon dioxide binding as cell waste. They'll bind and kick even more oxygen off of the hemoglobin. It's good because if you have increased levels of carbon dioxide, you probably need more oxygen. How to affect the release of oxygen causes a conformational change in hemoglobin. Conformational change increases the amount of carbon dioxide that can bind. So just as oxygen binding causes more oxygen molecules to want to bind to hemoglobin or makes them able to bind to hemoglobin, oxygen releasing makes it easier for carbon dioxide to bind, as well as oxygen to release. So the conformational changes are very much working in the gas exchange favor. Okay, we can call shift to the saturation curve. So some variables will decrease oxygen affinity for hemoglobin, and that causes a shift right. So that hemoglobin curve, that kind of curve that we were seeing, if you shift it to the right, you're decreasing your oxygen affinity. So increased temperature, increased in hydrogen ion. Other variables will increase oxygen affinity to hemoglobin, causing a left shift. So the colder it is, the less active you're going to be, the more your body the more the hemoglobin will hold onto the oxygen. Here is just a depiction of that, some of the different changes that will happen to cause the curve to shift left or right. Hyperventilation, breathing rate above the body's demand, anxiety, ascent to high altitude, or it's voluntary. Your PO2 rises, PCO2 falls in the alveoli. An additional oxygen does not enter because hemoglobin is already 98% saturated, but a greater loss of CO2 from the blood caused hypocapnia. So hyperventilation, increased PO2. Start to make your blood alkaline. Low blood CO2 causes vasoconstriction. So as you're increasing your oxygen, you're decreasing your carbon dioxide. It's causing vasoconstriction, so the brain vessels may constrict, decreasing delivery to the brain. Decreased blood hydrogen ion concentration. If buffers can't compensate, again, it's respiratory alkalosis. Hyperventilation can cause feelings of faintness or dizziness, numbness, tingling, cramps, and tetany, so muscle contraction. If prolonged, you get disorientation, loss of consciousness, coma, and possibly death. Hypoventilation, breathing too slow or too shallow, bradypnea, or hypopnea, causes airway obstruction, or causes include airway obstruction, pneumonia, brainstem injury, or other respiratory conditions that will cause your oxygen levels to drop, your CO2 levels to rise. Blood PO2 decreases, hypoxemia can lead to low oxygen in tissues, which is hypoxia, and blood CO2 increasing, which is hypercapnia. Lots of fun words here. So hypoventilation can result in inadequate oxygen delivery, result in increased hydrogen ion concentration due to high blood PCO2, giving you respiratory acidosis. Again, this is respiratory because we're talking about the respiratory system. Can cause lethargy, sleepiness, headaches, polycythemia, cyanotic tissues due to loss of oxygen. Convulsions, loss of consciousness, and death can result from hypoventilation. While exercising, the breathing is hyperpnea to meet increased tissue needs versus eupnea. The breathing depth increases while the rate will remain the same. So you won't actually take faster breaths, you'll just take deeper breaths, which a lot of people don't realize until the next time you exercise. Blood PO2 and blood PCO2 will remain relatively constant. That's homeostasis. So even during exercise, they should still remain about the same. Increased cellular respiration compensated for by deeper breathing, increased CO, greater blood flow. The respiratory center is stimulated by proprioceptive sensory signals to movement, motor output from the cerebral cortex, so you're kind of consciously trying to breathe deeper, and conscious anticipation of exercise, knowing that it's coming.